Okay, so welcome. My name is Nicolas. I'm from Switzerland. In my day job, I'm doing embedded devices security analysis. So it's mostly about software and hardware evaluation, side channel analysis, fault injection, all this kind of stuff. And by night, I'm basically doing the same, but with way less money and trying to find ways to, find new ways to do side channels or hardware evaluations, but with less money.
Okay, hello. I'm Benjamin Vernoux. So I work mainly on embedded hardware, and I'm more specialized at start on embedded firmware. And there I have developed different open source tools like AirSpy, for example. I have done the conception of all the AirSpy R0, R2 Mini on the hardware side, and on the firmware side, also OS tools. So everything on firmware, everything is open source, and also Hydrabus V1 with Hydra NFC, which is open source software. And the new one is Hydra USB 3. And also the hardware we will present you today. So let's start. So what is EMC? It's electromagnetic compatibility. So it's ability of electrical equipment and system to function acceptably in their electromagnetic environment. So device under test, DUT, behave normally in case of electromagnetic interference, EMI. So does the DUT generate EMI? It's a question. So it's mandatory for commercial products. So let's see different types of EMI coupling. So we have both different ones. So we have radiative. We will see another slide. It's mainly antenna. We have inductive coupling, and we have conductive and capacitive. So radiative coupling, it's when an unwanted signal is transferred from source equipment to victim's equipment by radiation from space. Inductive coupling is the source and the victim are coupled by magnetic field. You can see there. So conductive coupling, it's what we will see today in details. It's the purpose of the talk. It's where there is a conduction route along with the signal can travel. This may be along power cables or other interconnection wires, and the conduction may be in one of two modes. So we'll see that after. And then capacitive. So let's see type of EMI coupling, radiative. So we'll focus on that. Like you see, there is some near field probes, which are well-known tech box, for example, which are used often for EMC analysis. So the purpose is to capture radiated emission measurement from less than 1 MHz up to 6 GHz, and it includes a preamplifier. So this type of probe can be used with an oscilloscope or a spectrum analyzer. So let's see, it's my personal antenna for test. So it's for radiative, again, it's ultra-wideband antenna, or low periodic antenna, like this one. So the aim is to have very big range for test, for under 400 MHz up to 6 GHz from RF space. with a gain which is 4 dBi. And this one, which is more portable, it's about the same range with gain a bit better. So it's very good on field to test EMI. So our assumption and why we are here today. So radiated and induced EM emission can already be used to perform side channel analysis. Can conducted EM signals do the same? Couldn't find any reference in academic papers. Usually a bad sign. So only one way to find out, testing. So let's see EMI coupling conductive. So what we have is the power supply with a power cable connected to the DUT, device under test, also known as equipment under test. So what we have basically, just this cable. What we will add is a capacitor, which is a DC block, and an EMC analyzer. So what happened in that case? As the power supply, the impedance is unknown. So if low impedance, we will have low voltage. So it's not good. And if we have high impedance, we will have high voltage there. And the DC coupling is here to filter a DC current, to just have alternative current there from few kilohertz to more than 200 megahertz. Okay? So there, the issue is here with this schematic. So let's see how to improve that. To improve that, we will use something you probably don't know because it's very specific. It's a LISN. So the LISN is a line impedance stabilization network. It's mainly used for EMC testing. So what it does, it does a low pass filter. For in our example, it has cutoff frequency of 250 Hertz to let pass only the DC, in fact, as we want to filter any noise from the power supply. So it's typically placed between a power source and the supply terminals of the device under test. Used in EMC testing, like I told you, provide a well-defined RF impedance to the DUT. What we want is to match it to 50 ohm impedance. So why for 50 ohm impedance? Is to have the lowest loss maximum power transfer in RF, in radio frequency, captured with an oscilloscope or a spectrum analyzer. Today we will see only oscilloscope because spectrum analyzer is not very useful for side channel analysis. So it also do filtering on power supply noise to remove it from the measurement. So we see a basic schematic. We have power source, it enters the LISN, then it goes to the device under test to power the device, and then we have conducted noise, in fact, which come back to a DC block, and we have a spectrum analyzer or an oscilloscope. So let's see what is the LISN. So the LISN, like explained before, allow to have a 50 ohm impedance over more than 100 megahertz, but even at 2 megahertz, we have 50 ohm. We will see after. The objective, the aim, is to even exceed 200 megahertz to do the side channel analysis, side channel attack on the DUT. So there we see the power cable. There it represents the filters, and there we have the inductors, in fact, to match to 50 ohm. And there's the EMC analyzer. So an important point with the LISN, it's about a big warning about the PSU, the power supply unit, because of transient voltage. When you power on or power off your power supply, you have a transient which go directly and pass the DC block and will destroy your spectrum analyzer. So it's very important point to check how to avoid that, as it's quite expensive hardware. So to show you how to protect about that in a standard LISN. So we had a transient limiter, example like mini circuits. They are very good ones with insertion loss 0 dB, and it acts as a limiter to plus 10 or more, in fact dBm. It's to protect the EMC analyzer. Then we can add a preselector, which want to filter, remove unwanted frequencies for analysis. And there we can also add a preamplifier to recover the signal loss because of the preselector and potentially the low signal there. And then at the end we have the EMC analyzer. So let's present commercial LISN are quite costly, about 400 euro. The well-known one, which is DC 4 microhenry LISN, are tech box DC LISN. So to have a full LISN dual, to have both sides, plus and minus. We will see after why to have both. We need 2 boxes like that, so it's about $500 US. So let's build our own. It's one I have built, and it's open source hardware, and there with the filter. So it's just equivalent to the TechBox one with more protection, in fact. And then there you have also dB insertion loss to lower the power. So LISN for side channel analysis. So LISN usually have attenuators to avoid damaging measurement tools, might dampen the signal. Standard LISN output is 50 ohm matched, so cannot use oscilloscope with 50 ohm termination. Requires a transient limiter to avoid potential damage, permanent damage to the oscilloscope input. So must use an 50 ohm impedance adapter to connect to oscilloscope 1 megaohm input, for example. For low-cost oscilloscope, which don't have 50 ohm input. So what's the solution? The solution is to remove the attenuator and add input protection. We will be using an oscilloscope anyways. So let's see the conception of DC LISN for side channel analysis. So we will see the simulation of the low-pass filters and 5 microhenry inductors using QCS Studio, which is freeware for .3.1. So there we see a very basic simulation with a filter with a capacitor there, with a small damping resistor of 1 ohm. And there we will add another capacitor to filter other frequency. It's 2.2 microfarad with a very small resistor. And then again another capacitor, so 2.2 microfarad too. And there the core of the LISN is the inductor, which is a about 5 microhenry. So there you can see the different steps on the frequency. It's the frequency response, we call also insertion loss in decibel. So we start at 0 because it's DC. So we want all the power to power the DUT, and then we want to filter at maximum all the frequency which are the we don't want any perturbation from the power supply. So we try to take this curve at lowest as possible with those filters. So we will continue with LT Spice. Why I change the tool? It's also open source tool. No, not open source, but free tools from Analog Device. It's just because, in fact, we can do better simulation with some characterized inductor, for example, there. So it's a bit better for the simulation. You see the curve is practically the same as before. So we see the effect of the inductor there at 100 megahertz. So let's see the different effect on the low pass filter on the input. For example, if we just add a 22 microfarad capacitor, very basic filter, we see it's about minus 30 decibel attenuation at from 10 kilohertz. Okay, with this curve. So it's not very deep. So we add another one there. We add in fact 2.2 microfarad capacitor, and we see how it improves the frequency response to the insertion loss up to minus 80 dB. It's simulation. We will see after. It's not the reality, but we have an idea. And if we add also the inductor, we see also an effect on the filtering, which appear about at 1 megahertz, because the inductor also acts like a filter, and not only impedance impedance adjustment to have 50 ohm, but it acts also as a filter there. And then I have also added a very big capacitor, 1000 microfarad, and we see the effect even on the very low frequency. We gain about 30 dB. See, be 20 to about 20 dB until just before 1 megahertz. So it could be also a very good improvement, depending on your power supply, to add such capacitor as input. So let's continue the conception of the DC LISN. We will use KiCad. As I said, I use only open source tools for everything. So, like we have seen before, we have a 22 microfarad with a resistor. It's a low, with 2.2 microfarad capacitor there. We have two. It acts as a low pass filter with a cutoff frequency of 240 Hertz about. It's not very accurate, it's simulation. And there we have 5 high current inductor up to 15 amp, and each one is 1.1 microhenry to have about 5 microhenry at the end. And there we have the DC block. So you see on the side also DC block, and there is a protection. So there is a different protection. on HF plus and HF minus. In fact, this schematic it shows just one part, but there is exactly the same on the minus part. There it's DUT plus, but I have removed it. It's exactly a clone of this one for the other part. So we have very strong protection to protect your expensive oscilloscope or spectrum analyzer to be connected on HF plus there. So we start with a GDT, which is a gas discharge tube. It's mainly for lightning disturbance, so it's very strong to avoid lightning disturbance up to 5 kiloampere and 65 volts. It starts to protect. When you have such condition, in fact, the strike goes directly inside the gas, which avoid to damage the precious spectrum analyzer or oscilloscope there. So after that step, it protects also other sensitive protection. That's why it's the first. We have BIV99. It's a high-speed diode, well known because it's very good to be used as a limiter and to clamp the signal we have in input to 2 volt peak. And then after this one, we have another ESD protection for transient voltage suppression. So like that, you are fully protected, and you will never exceed 2 volt peak on the input of your oscilloscope or spectrum analyzer. I will show you after in practice. So yes, all those have been tested with a signal generator and power supply 40 volt. We switch on, switch off in practice to show it's very effective. Okay, so we will see the conception of the PCB under KiCad 6. So what's the main in fact, what we will focus is to have an impedance of 50 ohm on the pass there. It's like I told you, it's the same part there and there. It's for plus, and there it's for minus voltage. There you have the PSU, which is connected. There it's a earth ground. Okay. And we try to match this PCB with Saturn PCB toolkit, which is a free tool also, which allow you to compute the impedance to have 50 ohm. So you can compute the conductor whites. It's whites of the conductor there and there, depending on the pass. This pass or this pass one is for the spectrum analyzer there. You connect on plus or minus. So at the end you have a box like that. So you can connect your oscilloscope there on one of these ports, and you have a warranty to have a 10 dBm limiter there to don't even if you have strong pulse or strong noise appearing, you will never exceed 10 dBm. So let's do some measurement with the standard CSPR25. It's the standard for EMC on automotive. So we will check we are compliant with this standard. We can check that with VNA. It's a very expensive device. It's a vector network analyzer that I have in my lab. So it's HP. I will show you after. It's funny, old school hardware. And we match perfectly the curve from 100 kilohertz up to 100 megahertz, even if we go higher, in fact. But for the standard, it's not required to go higher. And we see the impedance is exactly in the middle in the measurement. Okay, so here we just see with the VNA the different measurements, with the measurement of filter, insertion, isolation, up to 1 gigahertz. There it's even 6 gigahertz. So. And there we see the measurement, insertion bandwidths and cutoff frequency between the DUT and the HF plus. There, it's where you will do the measurement. So DUT is your device under test. And there it's where you will connect your oscilloscope. So there, we see it's a very, we have about 400 megahertz bandwidth. So it's interesting to do side channel up to frequency more or less than 400 megahertz. And then here it's a check of the limiter clamp, which is a very important point to avoid to burn your oscilloscope input or spectrum analyzer, like we see there. I put a signal of T volt peak, and there we limit it limits the signal as output, which is there, to less than 2 volt peak, so about 10 dBm. So let's see the measurement setup.
Okay, so now that we have a device for measurements, how does it work, or how do you make it work in a setup? There's a standard CIS PR25, which is unfortunately not free. You can still find some versions of this documentation using Google, but you can also find this documentation for other LISNs in the user manuals of those LISNs. They give you information about how to use those, and it usually looks like this. So what you have to do, where is it? Here, yeah. So you have your power source, you have your two LISNs connected on the VCC and ground lines, and then you have your device that you want to test. What is really important is the length of the cables. So here it has to be less than 20 centimeters. The device has to be at least 5 centimeters above what they call the ground plane, which is a conductive material directly connected to Earth. That way it will remove some of the parasitic noise that you might have in your lab. So I did more or less the same. So I took an STM32. I removed all the decoupling capacitors, the things that you usually do when you want to do side channel analysis. I installed the LISN on both lines. I used my personal oscilloscope to get the traces, connect the ground plane, connect to Earth, make new cables because mine were too long, and then just connect a USB to UART to my PC on the DUT. And here you might see there is a problem, because when you are connecting your UART to the DUT, basically you are bringing noise from your PC to the device, which is not good. So what I did first was to use optocouplers, which is basically a way to transfer signals without an electrical connection between the DUT and my PC. And then I used digital isolators. Those are chips that basically do the same but way faster. As an example, this is a direct connection. So the device is off. It's just the pure noise of my measurement setup. So with a direct connection with my PC, it looks like this. With the isolator, it's already way less. And if I connect the ground plane, it's even less. So you already see an improvement of your quality of the signals using this kind of setups. The final setup I did is looking like this. So you have the LISN here, my DUT is here, this is the isolator, this is my USB to UART connection, and you don't see it, but this cable goes to my oscilloscope. On the software side, I use the software SM4 implementation. You will see that tomorrow. We have another talk with somebody else about SM4. It's not that I'm lazy, but let's say if I could do two measurements, one measurement for two talks, it's even better. So if I'm running the capture, I have this kind of signal on my oscilloscope, and if you count, you have 32 peaks, which corresponds to the 32 rounds of SM4. So it looks like we have something to work with from the side channel point of view. The next question is, okay, we have some signal, that's good, but how is the signal better than a simple shunt resistor, the thing that you usually do with simple power analysis? So what I did is get the exact same setup, but instead of the LISN, I just put a small 1 ohm resistor on the line and did the same capture. So as a reminder, this is with the LISN. You can see the vertical resolution is 5 millivolts per division. And with the 1 ohm resistor, not that good. You can see that now I had to zoom on the vertical scale to have a better signal. Doing a correlation power analysis on the SM4, what I did is I took 5,000 traces, both with the LISN and with the shunt resistor. So those traces were fed into the script that we will present tomorrow to find out if we can recover the key using this power analysis. And it turns out that with the LISN, you can see that there is a small peak here, which corresponds to 1 key byte of 1 key byte in the first round, and it's correct. But on the shunt resistor, you don't see that small peak. That means that I was not able to recover part of the key using this information. If you have more traces, it will work, but with only 5,000 traces on the LISN, you can at least get 3 out of 4 bytes of the key, which is already good. But with the shunt, I had no correlation. So it looks like the dynamic range with the LISN is a bit better and it allows to recover the key. But this was, let's say, the ideal setup. I removed all the capacitors. It's an old microcontroller. It leaks a lot. So maybe with more recent chips and with more difficult parameters, it will not work as good. So I did another setup, which looks quite the same. The only difference is that I used an ESP32 dev kit, and this time I did not remove any capacitances or nothing. It was just the out of the box placed on my setup. Used a different firmware. This time I used software AES because it's more common, and all the rest is exactly the same: the LISN or the 1 ohm shunt resistor. I had to use the 1 ohm resistor because if I tried with a larger one, I used a 10 ohm resistor, and unfortunately the brownout detection of the ESP32 was triggering, so the device was rebooting every time. This time the traces are not that clean. So what I did is I took 50,000 traces. For every traces, it's an average of 1,000 times calculating the AS. So it's more 50 million acquisitions that were averaged to get those traces. Every time it's the random plain text. I did no synchronization, and of course, using the CPA, it works perfectly fine. So you can see there's a peak here for this byte of the key. That means it works. So here on the left, the graph represents the time and the correlation value for a specific key bytes that you want to recover. On the right, what you have is, for every key candidate, the correlation value based on the number of traces on the x-axis. So the more traces you have, the more correlation you will have, so the more confidence that it's the correct key byte you will be. So to compare both, looks quite the same. So you can see, you can get the key byte. It works perfectly fine. You can already see that on the shunt resistor here, this, which is the correct key, is a bit higher than the others compared to the LISN. So now, how do we compare this? Unfortunately, I didn't find any way to correctly compare two trace sets or techniques to discover this. So what I did is a simple signal-to-noise ratio. So what I'm using is, for a specific number of traces, I will take the correlation value for the right one over the mean of all the others. This will give me a number, basically how much the correct key rises above the rest. And to compare this, I did all those measurements of the 50 million traces times the LISN times the resistors. So my oscilloscope was working quite hard. And to compare this, you have the LISN in blue and the shunt in kind of orange. I don't know. So you can see on the top one, it's the best case I had. So the shunt is gives a better distinguish for the key on the traces over the LISN. But most of the traces or the key bytes were mostly the same. So LISN and shunt in those cases are mostly equivalent. Just as a comparison, I did an FFT on the signal for both the LISN and the shunt. So you can see that the LISN is brings back a bit less signal than the shunt, but at least it still works, so that's good. As we mentioned earlier, the LISN provides the measurement ports both on the VCC and the GND lines. So I did again acquisitions of 50 million traces with the random plaintext, just to see if there was a difference between the ground and the VCC lines for the side channel. And of course I did the same with the resistors. So that's again 50 million traces more. And you can see that on the LISN, at least, you have a better chance of getting the key byte in some cases, but most of the time it's barely the same. Compared the same with the shunt resistor, the main difference here is that for the shunt resistor, the voltage that you read is around 0, so it's easier for you to retrieve the signal. But if you place the resistor on the VCC line, you still have your DC voltage. So I had what I did is I enabled the AC coupling on my oscilloscope, so that could explain why the signal is not that great. Another thing that we can do is with both the VCC and the ground line, we can calculate the difference between the two signals, and maybe this will give us more information. So there are different things the different circuits to separate the common and the differential signals. And unfortunately, the signal gets quite lowered. That's because it's only a passive separator, so it's not that good. From the test I did, on the common mode, I couldn't see any correlation for the encryption or the key. But for the differential mode, I had some kind of encryption. I did not do as many traces, but at least that's another potential use of the LISN.
So in conclusion, we see, LISN provides a different way of acquiring side channel information. So in practice, similar performance as a shunt resistor. Of course, a lower inline resistance because it's like 0 ohm on the LISN, so there is no effect on the DUT like you could have with a shunt resistor. And it could be useful for specific targets because it's non-intrusive and easier to set up on the side. You don't need to solder a resistor or things like that. And the signal is already AC coupled, and the measure is made on both lines. So you have the plus and the minus. Minus is ground on this case, but you can have power supplies with negative voltage also. And EMC testing methodology allow to enhance signal quality by diminishing the noise. So for hardwear.io, we have done a specific limited edition of this hardware. The latest one specialized for side channel, but it works also fine as a standard LISN. It's fully characterized with vector network analyzer. For example, I have some bonus where we show how we measure the different the impedance of the LISN, the insertion loss. We see the insertion loss is what you will lose when you measure the DUT signal. In fact, the leakage from the HF plus or it's HF or RF. The names or RF plus or RF minus. RF minus is considered as ground in this presentation. In fact, it's a ground leakage, and RF plus is plus the VCC leakage. So we see the insertion loss is very good, up to 400 megahertz. Even more, in fact, there is a small tip. Yeah. But it can go. In fact, the limitation is my test setup there. As a banana plug is not the best to have a good signal, but it's the only way to measure the insertion loss with a vector network analyzer. And there we see the isolation. So when the LISN with the filter and the inductor, we see more than 60 dB isolation. That's all. Thank you for.
Thank you, guys.